We shall now center our focus on what the binomial probability distribution is. Precisely, the binomial probability distribution is one of the many standard discrete probability distributions in statistics. If we are interested in counting X successes or X events of interest in N trials of an experiment, and certain conditions are met, such as 1, 2, 3, 4, and 5 on your screen, which we will soon go over, then you have a binomial experiment. The best way to review these conditions for a binomial experiment would be to take this example. This would be an appropriate guide or driving lamp for us to understand what's going on. So let's consider this question. In which of the following scenarios for computing probabilities can we say we have a binomial experiment? Select all that apply. For example, we're told that we want to compute the probability that 3 out of 8 tosses of a coin will result in heads. So the event of interest here is that when we toss a coin, it results in a head. So is this a binomial experiment? Let's test against these conditions. First, a trial of this experiment must have only 2 possible outcomes, hence the word by. The word by means 2. So whenever you toss a coin, you can either get, in this context, a head or a tail. So it means that criteria 1 is met by this scenario. But that's not enough to call it a binomial experiment. 2, how many times are you tossing this coin, or are you trying this coin? There are 8 tosses of a coin. This is a definite value or a fixed number of trials. So again, this scenario crosses off the second condition. Then 3, the trials of the experiment are independent of each other. Yes, when you toss a coin the first time, what you get on the second toss of the coin does not depend on what you get on the first toss. So they are independent trials. It checks the third condition. Then 4, whenever you toss a coin, the probability of getting a head is 50-50 in this case. And this will not change from one toss of the coin or one trial to another. So there is a consistency in generating successes and failures. That is, the probability of a head in this case, which is 0.5, will be the same from one toss of the coin to the other, or the probability of success will remain constant from trial to trial. This condition is also met. In particular, those are the major 4 conditions. The 5th one is just an adjoining one. It actually ties with 4. As long as those first 4 conditions are met, this will be said to be a binomial experiment. So we have a check mark here. This is a binomial experiment that we can derive a binomial distribution from. We proceed to the next example. In the next example, we are told that a random sample of 15 middle school students is obtained, and the individuals selected are asked to state their ages. Well, this is where we begin again. What is a trial in this case? It will be asking each of the 15 students to state their ages. So when they state their age, do they have only 2 possible outcomes or 2 possible ages that they can state in this scenario? The answer is no. So that means that this scenario does not even meet the first condition, because the possible answers we will get from the students cannot lead to just 2 possible outcomes, one age or the other, in this context. So this is not a binomial experiment. We move on to the next one. An investor randomly purchases 19 stocks listed on a stock exchange. Historically, the probability that a stock listed on this exchange will increase in value over the course of a year is 43%. The number of stocks that increase in value is recorded. Let's think through this. So in this context, we're interested in the number of stocks that increase in value. So if I pick of these 19 stocks, considering if I pick the first stock, you observe that within the context of this question, it will either increase or decrease. So I have two possible outcomes. That first condition is met. 2, are there a fixed number of trials? Yes, I am trying 19 stocks. So my N here is 19, the number of stocks I'm trying, and it is fixed, it is definite. So condition 2 is met. Condition 3, the trials of the experiment are independent of each other. Well, in this case, for the 19 stocks, there is no indicator of how the stocks might be connected in any way. So, as it stands, given the information we have, the trials are definitely independent. The behavior of one stock is independent of the other one. So, condition 3 is met. What about the probability that a stock will increase in value? We're told that historically, that probability is 0.43 or 43%. This appears to be the same for each random stock that is chosen for observation. So the process is also consistent, and the probability that a stock will increase in value is 0.43 from one stock to the other. So condition 4 is also met. As it stands then, it means that this is also a binomial experiment. We proceed to the next scenario. In this case, we are told that 4 cards are selected from a standard 52 card deck without replacement, and the number of hearts selected is recorded. So in this case, if we have a 52 deck card, of course, a 52 deck card is split into 4 suits. You have the clubs, the hearts, the diamonds, and the spade. Now, for the first heart, we're interested in the number of hearts selected. Well, for every card you pick of these 4 cards, it is true that you either have a heart or you don't have a heart. So, this is 2 possible outcomes. That is met. What about the number of cards? How many cards are we trying in this case? We are trying 4 cards that are selected at random. And that means we have n equals to 4, a fixed number of trials. Now, at this point, we want to check, are the trials independent of each other? Well, if I pick the first card out of 52, what I get when I pick the second card, does it depend on what I got on the first card? Not necessarily. Or maybe not. For now, let's say for the most part, it is not, just because we have n equals 4. So the trials are independent. Now, here's where there's a problem. These cards are selected without what? Replacement. So the first time I'm selecting a heart, the probability that the first card is a heart is 13 out of 52. That's for the first trial. But for the second trial, probably that the second card is a heart is no longer 13 out of 52. Why? The cards were selected without replacement. So if I selected a heart on the first pick, I am now down to 51 because I did not replace the first heart. And the number of hearts too has gone down to 12. So the probability of picking a heart from trial to trial under the conditions of picking without replacement is not the same. It is not constant from trial to trial. This event fails the 4th condition explicitly. And so this 4th one is not a binomial experiment. Then a basketball player who makes 88% of his free throws is asked to shoot free throws until he misses. The number of free throws attempted is recorded. Well, in this case, what we immediately have a problem with is that even though these can lead, every trial here can lead to two possible outcomes. Either he misses or he makes the throws. But do we have a fixed number of throws? In this case, we don't. We don't have a fixed number of throws. So this is not a binomial experiment because it misses on condition number 2. It violates condition 2. Then the last question says the probability that the student blindly guessing will get at least 8 out of 10 multiple choice questions. Well, if we're interested in the number of multiple choice questions that are gotten correctly, for the first trial, for the first condition, yes, it's either he's going to get it correct or wrong. Two possible outcomes. Then, are there fixed number of trials? Yes, he has 10 multiple choice questions. So our n in this case is 10. Then, what about the trials of the experiment? Every time he is guessing each question, what he guesses for the previous question does not dictate what he's getting on the next question. So the trials are definitely independent of each other. Then the probability of success for from one question to another, is it constant? As it stands, we are told that the probability that a student blindly guessing will get at least 8 out of 10 multiple choice questions correct. As it stands, this is either 1 over 2 or 1 over 2, depending on how many choices it gets for each question. So the probability of success is constant from one question to another. So in this case, this is definitely a binomial experiment. And with that, we have spotted the binomial experiments here. This is good, bad, bad, and good. These are the binomial experiments here. Once we identify a binomial experiment, we can then develop a binomial probability distribution model where, take note, we will talk about your n, that is the fixed number of trials for a binomial experiment, fixed number of trials, and then the p is the probability of success in one independent trial, Now, the probability for computing any of the possible values of a binomial random variable is given by this probability distribution function. So, to illustrate this, let's take an example. It has been stated that about 41% of adult workers have a high school diploma but do not pursue any further education. 20 adult workers are randomly selected. Let X equals the number of adult workers who have a high school diploma but do not pursue any further education. We are to find the probability that X, that number of adult workers, is equal to 2. In order to do this, first, we convince ourselves that this is a binomial experiment. Each adult worker is a trial here, and either they will pursue further education or will not pursue further education. So there are two possible outcomes here. 2, the number of trials we have here, n, is equal to 20 because we are trying 20 adult workers, and each of them is a trial that will lead to two possible outcomes: pursue further education or not pursue further education. Then the probability of success is the probability that a person, an adult worker, will have a high school diploma but will not pursue any further education. So that will be 0.41. And so we can say that our X in this case follows what? The binomial distribution, where your n is 20, just as illustrated here, and our P is equal to 0.41. This is a summary of the scenario. Now, since this is binomial, in order to find this probability, the probability that out of these 20, only 2 of them will have a high school diploma and will not pursue any further education, we can use this formula, which is n combination x multiplied by p raised to power x, 1 minus p, n minus x. All we have to do is substitute n is 20, combination x in this case is 2, times p is 0.41, raised to power x, x in this case is 2, and then 1 minus 0.41, then n again is 20 minus x is equal to 2 again. So we have 20 combination 2 times 0.41 raised to power 2 multiplied by 1 minus 0.41. 1 minus 0.41 is the same as 0.59. 20 minus 2 is the same as 18. So how do we get 20 combination 2, this value, and then this value? Let us see. In order to get 20 combination 2, what you do is, let's go to StatCrunch. You go to data, go to compute. Again, just to emphasize, go to data and then compute an expression and type COMB, combinations. And this time we want 20 combination 2, which means in how many ways can 2 be selected out of 20? So we have 20, comma 2. Close the parentheses and hit the compute button, and you have 190. So this number, this computation here, is equal to 190 multiplied by 0.41 squared multiplied by 0.59 raised to power 18. So on my calculator, let's see what I get. If you multiply 190 multiplied by 190 multiplied by 0.41 square multiplied by 0.59 raised to power 18, this is the answer I have. Well, in reality, you would not need to cram this formula. Let's see the alternative ways of computing this probability. As you might already guess, StatCrunch can help us to do this. So let's see how this is done in StatCrunch. So I'm going to go into StatCrunch, go to Statistics, Calculators, and in the sub-menu, go to Binomial. Click on Binomial, and you would like to set the parameters here. Let's go back to the question. Our n is equal to 20, and our p is equal to 0.41. These are your tuning parameters here. So we're going to set this to 20, and this is 0.41. And in particular, what probability would we like to compute? The probability that x is equal to 2. So I'll adjust accordingly. So I want probability x equals to 2. And I'll hit the compute button. And you can see it's right there for equal to 2. And the value is 0.0239694, which is the same as this. So subsequently, you won't need to remember this formula. You can actually use StatCrunch to generate the final result here. I guess that is definitely a huge relief, right? Okay, let's move on to another example. And in this case, we are told that approximately 70% of statistics students do their homework in time for it to be collected and graded. Each student does homework independently. That is the assumption of this problem. 10 students are randomly selected. If we let X represent the number of students who completed their homework on time, we would like to calculate the probability that that number X is less than or equal to 7. So what do? First, our X in this case follows the binomial distribution where N will be the number of students tried, that is 10, and P is the probability that a student randomly chosen would complete their homework in time for it to be collected and graded. And that probability is 70% or 0.70. So we would like to compute the probability that x is less than or equal to 7. I do want to encourage you, as a side note, to convince yourself that this scenario qualifies as a binomial experiment. With that said, let's go into StatCrunch and generate this probability. So we need n equals to 10 in this case. The probability is 0.70. Let's make sure we have the right one. 10 and 0.70. Then we want less than or equal to 7. So I'm going to change this to less than or equal to 7 and hit the compute button. So this will cumulate from 7 all the way down. All of these probabilities, and added all together, you have 0.6172. So I have an answer here. This is equal to 0.6172. Done. With that question completed, we proceed to the next example. In this example, we're told that according to flightstats.com, American Airlines from Dallas to Chicago are on time 80% of the time. Suppose 15 flights are randomly selected and the number of on-time flights is recorded. Let x equals the number of on-time flights. What is the probability distribution for x? Well, if x is the number of on-time flights, and we are talking about 15 randomly selected flights, you observe that for any of these flights, it is either on time or not on time. So it has two possible outcomes. That is the first condition for a binomial experiment. Then two, how many flights are we trying? Is it a definite or fixed number of trials? Yes, because our n is 15 here and it is fixed in this case. So condition 2 for a binomial experiment is again satisfied. 3, we would like to check if the trials are independent of one another. The truth is, what happens with one flight is definitely independent of another flight. So the trials are independent. Then 4, we are told that on the probability that a flight from Dallas to Chicago will be on time is 80%. So the probability P in this case that a flight will be on time from historical data evidence is 0.80. So we can say that the probability distribution of x is definitely binomial, where our n is 15 and our probability of success is 0.80. What values does x take? Well, the possible number of flights that are on time out of this 15. I can have, in the worst case scenario, 0 out of these 15 flights were on time. I can have 1, I can have 2, as much as 15. So take note, the highest possible values of x will be the value of n. That is a great hint to note. Then next, we want the probability, capital P, that the number of flights, x, that will be on time is exactly 10. So we go to StatCrunch. We're going to key in our parameters, n equals 15 and p equals 0.80. So we have 15 and 0.80. And next, we are interested in equal to 10. So let's adjust that, equal to 10. And compute. And that value is 0.1032. So we have that, 0.1032. Then the next question says, what is the probability that at least 11 flights are on time? In other words, x, the number of flights that are on time, is at least 11. At least 11 will be equal to 11 at the very least, but it could be greater. So we head back into StatCrunch, and we're going to change this to greater than or equal to 11 and hit the compute button. Notice that I did not change the parameters because it's still the same problem with the same parameters in this case. So we have 0.8358, 0.8358. And then what about the probability that the number of flights that are on time is between 8 and 10, keyword inclusive? So this might be more instructive. The between is taken care of by the less than. Then the inclusive means I have to include 8 and 10. So take note, what happens in this case? I am interested in from 8 to 10 and 9. These are the probabilities I would like to collect together. So let's see how to do that. To see how to do that, we'll need to tweak the interface that we're working with currently. So let's go back here. And the first thing I'd like you to do is to choose this option, which is between. Then you'll see that the graphical interface here will change. We're going from equal to 8 up as far as 10, based on our interpretation of the question. So we can compute. So this is 0.1599999. This is approximately 0.16. So this is equal to 0.16. And with that, we've come to the end of this video. So in the next video that will follow next week, you will expect us to go a little bit deeper into binomial probability distribution functions, the mean, the variance, the standard deviation, and how the binomial distribution is applied in real life.